Okay, so start. Okay, so partial differential equations. So it's PDs. So we'll try to develop some develop some numerical strategies to solve PDs. Okay. So you already know PDs arise in many branches like fluid dynamics, heat transfer, and definitely is being used in R&D sectors. Okay. So wherever you go in R&D sectors, for example, mainly in ISRO's, okay, mainly when the rocket is carrying, like going up, you are trying to understand how the heat is changing of the rocket, like towards the end, towards the engine, and how much it is spreading where. Okay. So if you see some abnormal distribution of the heat, if you see some abnormal distribution of the heat, then you can say that no, my system can go uh, like haywire after some time of the release of the rocket. Okay, so in that way, PD has been able to save a lot of lives also. Okay. So you can predict anomaly situations through PD if you consider the heat distribution or heat flow in different rocket situations. Okay. So another case is also you can see like fluid dynamics in the dam. For example, the recent work that is going on is something like you have a dam, and actually the floods actually happens when the dam breaks. When the dam breaks, actually, because when the dam breaks, when it contains more water than expected, that means you are having a flood type of situation, and water is getting concentrated. And you, as you know, what's the heaviest thing you can create right now? In this situation, in a classroom, may I ask you a question? What's the heaviest thing you can create quickly? Is water. Because 1 liter of water is nothing but 1 kg. Okay. So therefore, you can just bring in water and you can create big mass. Okay, big weights. Okay, more than your weights. You can, I mean to say that you can collect water and make larger masses by yourself. So why it is important? It is important to say that when water is contained in your dams, there is a limit the dam can hold the water. After that, it will break due to the force of the water. So when it breaks, suddenly flood comes in. And when the flood comes in, you know there is disaster, right? So therefore, the question is, can we predict at least some few hours before or at least one day before that, yes, this is going to happen? You understand the scenario, right? I don't want to predict like, yes, after 30 minutes, the dam is going to break, because I know within 30 minutes, I cannot take people anywhere else. Isn't it? I cannot take people from one city to another city within 30 minutes. Definitely water will consume in it, right? So can I predict that scenario or anomaly before? You know, you understand, no? So at least one day before. How can I do that? So this is the case where PDs and AI, they come together. AI will, like neural PDs. There are something now trending right now is neural operators, where you are using neural networks, okay, and AIs into this AI assisted deep learning techniques to this PDEs. It will get these physics informed things to the AI, and it will try to predict when the dam can break or when the water can go. Okay, so this is very recent research I heard from one of the faculties. Okay, so which is quite interesting. Okay, fine. So but the most difficult part of PDE, very less PDEs, very less, I mean, not a good word, very few PDEs have analytical solutions. Okay. I mean, very few PDEs you can solve analytically. I mean, you can use some mathematical techniques which you know already to solve the PDEs. But otherwise, there are all numerical methods to solve PDEs. Okay. So that's the case we are coming into. We want to develop some numerical methods to solve those PDEs. Okay. And the simple idea is discretization. Simple idea is discretization. Okay. So how to discretize PDE and then predict the future based on the past. That's what we all are doing. Okay. That's what we knew many years before, and that's what AI and neural network is doing. It is predicting based on the given data the future trends. Okay. So the same our numerical methods and iterative schemes are doing it. Okay. So fine. So to solve it numerically, okay, numerically we use the method of finite differences. The method of finite difference to obtain numerical solutions. To obtain numerical solutions. Okay. Fine. So we'll start like let's start with some PD. Let's classify different types of PD we have. Different types of PDs. Okay. PDs, right? So a general PD I can write is a general PD has this following expression. Okay. So with two independent variables, with two independent variables takes the form. Okay. It takes the following form, like you have some function ax, y, which is a function of both x and y, and you have a partial derivative with respect to x2 twice, second order, dou to u by dou x2. Okay. U is a, mind you, u is a function of both x and y. U is a function of both x and y, and the job is to find u, the solution. Same in differential equation also we did like that, right? So can you tell me another term? So we will have another term that is a mixed partial derivative, right? I hope you have seen these things in optimization also. Okay. Then what else can we have? Dou to u by dou y2 also we can have. With respect to x, the double derivative, with respect to y, the double derivative, a mixed derivative we can have. Then all other terms I can squish down into, like, say, here, like, it can also have this first order derivatives also. So have we covered all cases? Have we covered all cases listed here? I think so, right? Because we have considered dou u by dou x, we have considered dou u by dou y here, we have considered linear function of x u, we have also considered a linear function in u, and we are only considering the second derivatives here to note it down. Why we are doing that? Because the classification of various types of PDE depend on these second orders. This is the reason why we are showing them more appropriately than others. You got the idea, no? This is the reason why we are showing these guys more than these guys. Because the red ones helps us to approximate different types of PD. You will see that. You will see that coming. Okay. So let us try to, suppose this is PD given to you. Now, when can you say that this is an elliptic PD? When can you say that this is a parabolic PD? When can you say that it is a hyperbolic PD? Okay, there are three types of PDs. Okay, elliptic, parabolic, hyperbolic. Okay, we will not understand all of this in this course. We will study only one or two examples of them. Okay, but it's good for you to know. Okay, so how to classify? Let's see. Okay, this is the important case. Okay, so it is a elliptic PD. Okay, we'll see elliptic PD. If you have this b square minus 4ac, the quantity is less than 0. You understand the idea, no? See, all this quantity, it is an elliptic PD, b square minus 4ac is less than 0. Okay. Why? Because if b square minus 4ac is less than 0, automatically you know that some complex things will come into picture. That should ring a bell in your mind. Okay, complex things should come. And if when complex things come, you have two parts, that is real and imaginary parts. And if the real and imaginary parts are there, you will see some rotating waves. So rotating, it will rotate like ellipse. Okay. So that's what it is now termed as an elliptic PD. The solution will be like of ellipse. So this is the motivation why if you have b square minus 4ac is less than 0, it will something will be complex. I am not telling you exactly what is going to be complex because that is very deep. Okay. I don't want to explain that deep to you, but something will be complex because you can make a relation with the quadratic equation root over b square minus 4ac. So something will be complex, and something will be complex. That if something is complex, then mind you that it will create some rotation things. It will create some rotation things. Why? Can you tell? If something is complex, why I tell that you can have some rotation aspect? Because any complex number you can write in terms of r e to the power I theta. Yes, that means it has a radius. It has a radius. At what angle it goes, that theta is there. So it will always have a rotational aspect to it. Okay. So whenever, so now can you understand that if b square minus 4ac is less than 0, why it is called elliptic? I mean, intuitive argument do you have in mind right now? Yes. Yeah. Okay. Fine. So if it is a parabolic PD, okay, it is a parabolic PD if you have b square minus 4ac is equal to 0. Okay. Yes. If you have b square minus 4ac equal to 0, it behaves something like a parabolic kind of thing. This I cannot give much intuition. Sorry. Okay. But I can give more of intuition for elliptic. If you want to go very deep into this, then we can understand all of this. Why, if b square equal to b square minus 4ac equal to 0, we call it parabolic. Why we call that elliptic? That we have to go very deep into PD. Okay. And I suppose that this already has been covered. This already has been covered in your BSc degrees. Okay. Hyperbolic PD. So you will call hyperbolic PD if b square minus 4ac is greater than 0. Okay. If b square minus 4ac is greater than 0. Okay. If b square minus 4ac is greater than 0. Now I am trying to ask a question. Okay, this is the question 1 to you, that classify the following PD. Classify this PD as either elliptic, parabolic, or your hyperbolic. Okay. Can you classify this PD as parabolic, hyperbolic, or elliptic? Just you have to find what is A, B, C. Okay, and all other things you keep it on the right as F. Okay, so try to put this equation in this frame, and then find what are A, B, C, and then determine the sign of b square minus 4ac. Okay, so you can see this is 1 multiplied by this. So what is A? This is A. Okay, what is B? This is B, right? And what is C? This is C. And what I can do, these things I can put as F of dou u by dou x, comma dou u by dou y. Isn't it? So what is b square minus 4ac? What is b square minus 4ac? So what is it? Yes. So you see that b square minus 4ac is equal to 0 here. That implies it's a parabolic PD. Finish. Okay. That's it. That's it. So now you know that classification of PDEs depend on the double partial derivative with respect to x and y, and the mixed second order partial derivative. Other cases doesn't affect the classification of PDEs. Isn't it? I mean to say that even if you put it 10, 20, still it will be a parabolic PD. Isn't it? It doesn't take into effect that. I hope that is clear. Now, maybe I can do another question. So classify this one. X square dou to u by dou x2. Okay. Plus 1 minus y square dou to u by dou y2. Okay. Equal to 0. Given that x is from minus infinity to infinity and y goes from minus 1 to 1, can you classify this PD? Okay. As usual, this is your A, this is your A, this is your C. There is no B. B equal to 0. So since B equal to 0, minus 4AC. Okay. So what you will see, minus 4 times A, that is x square, into C 1 minus y square. Okay. But mind you, what is the sign of this quantity? So B square minus 4AC is this. So what is it, greater than, less than 0, greater than 0, or equal to 0? Which one? What do you think? Hmm? Why? Yeah, it is easy. What is this problem? Y is in between minus 1 and 1. So therefore 1 minus y square should be less than 1 only. Okay. I mean, it will be positive. It will be positive. 1 minus y square will be positive only. Okay. So x square is already positive. So minus sign is there. So it will be negative only. Isn't it? Yes. So if it is negative, it is a, yes, it's an elliptic PD. These are two examples where it is shown that what happens in the case when the A, B, C are constants, and what happens in another case when you see this A, B, C are the functions of x and y. We have considered two different examples here. No, x is a variable. X is a variable. You are differentiating with respect to x. X is not a parameter or something which you can set to 0. X is a variable, dou u by dou x. If x is 0, there is no meaning of dou u by dou x. Mind you that u is a function of x and y. Okay, u is a function of x and y. You cannot set x equal to 0, y equal to 0 as it is. Okay, I hope that is clear, no? So, yes. So actually there are two famous equations, okay, elliptic equations. Let us see elliptic equations for now. So you know what are elliptic equations? If you have b square minus 4ac less than 0, that is elliptic equations. Okay. So there are two famous elliptic equations that we are going to look at right now. Okay. There are two famous elliptic equations. Okay. So one is known as the Laplace equations. Okay. Laplace equations. Okay. I mean, x cannot be set to 0 like a constant. X needs to vary. If x varies, x can vary from minus infinity to infinity. If y varies, y has to vary from minus 1 to 1. Y cannot be kept constant. X cannot be kept constant. If x and x is constant, there is no meaning of dou u by dou x. What is dou u by dou x? Meaning? What is the meaning of dou u by dou x? How u changes as x changes. How u changes as x changes. But you are telling that x we can fix constant. Then how u will change? U will also be a constant. Then there is no meaning of PD. Are you getting the main agenda of this? Are you getting the main agenda of this? Not getting. U is a function of x and y. What does it mean? If you have x and y here, okay, there is a surface for each point x comma y, there will be a particular value of u. Yes. So what will happen if you cover this grid of x and y points? What will happen? It will have a surface of u value, no? For each point of x and y, you have a point in u, isn't it? Agree? So think of it like a paper. Think of it like a paper, like this. Okay. So think that, yeah, this one. This paper is x and y. This paper is u. This paper is x and y. This paper is u. Right? Yes. So u is a function of x and y. U is a function of x and y. But you are telling that x will be constant. If x will be constant, will you have this area? I am asking simple question. If x is constant, will you have this plane? No, you will have a straight line. X is constant. X is constant means you will have this only, no? Isn't it? You will not have a plane. If you don't have a plane, you don't have a y. Y will also be a line. What is the meaning of it? How many of you understood this? Okay, so elliptic equations. Okay, elliptic equations are of two famous types. Laplace equations you will see. Okay, and another is Poisson. Okay. However, we will look into the Laplace equation in this course. We will not look into the Poisson equations, but you can apply the same methods which we learned in Laplace equation in the case of Poisson equations as well. So what is a Laplace equation? Anyone? Cannot hear. Yeah? Grad to u equal to 0. The grad to u means what? Grad to operator is nothing but dou 2 by dou x2 plus dou 2 by dou y2 operator. Okay. So when you apply to u, what happens? Del 2 u by dou x2 plus dou 2 u by dou y2 equal to 0. So this equation is known as the Laplace equation. So we will learn how to solve this equation numerically. How to solve this equation numerically. Okay. What are Poisson equation? Poisson equation is nothing but the right hand side won't be 0. The right hand side won't be 0. So Poisson equation is like dou 2u not equal to 0. That means dou 2u or dou 2u will be some function of x and y. Okay. So what does it mean? Or dou 2u by dou x2 plus dou 2u by dou y2 equal to f of x comma y. So this is known as a Poisson equation. So what you see the difference between equation 1 and equation 2? What's the difference you see? The difference is the right hand side is not 0. Okay, if the right hand side is 0, it is a Poisson, sorry, it's a Laplace equation. If the right hand side is not 0, but a function of x and y, it's a Poisson equation. Okay. We will learn a numerical method scheme to solve this Laplace equation, and I suggest that you go back and try to understand, go to different books, and you will see that the same method which we learn can also be applied to the Poisson equations. Okay. So we understood. So what we understood now, we are concentrating on elliptic equations. Okay. There are two famous elliptic equations. That is known as, one is Laplace equation. Okay. Laplace equation, how Laplace equation looks like? You have grad 2 equal to 0. That is the partial derivative with respect to u of both variables equal to 0. Okay. Dou 2u by dou x2 plus dou 2u by dou y2 equal to 0. And another is Poisson equation. Okay. What is Poisson equation? You have dou 2u by dou x2 plus dou 2u by dou y2 is equal to some f of x comma y. Okay. Fine. So good. So actually, you already know about this in your, maybe in physics classes also. Laplace equation you might have seen in various electromagnetic problems. I hope the Coulomb potential and all those things, you might have heard this when you have some who are taken physics minor and all. Okay. And the Poisson equation actually comes up with some fluid dynamics problems. Okay, fine. So just for your knowledge. Okay, nothing much. Fine. So let us come back. Okay, fine. So actually, the solution of these equations, okay, the solution of these equations, that is dou 2u by dou x2 plus dou 2u by dou y2 equal to 0. So what is the aim? The aim is to obtain solution ux comma y, isn't it? The aim is to obtain the solution ux comma y, right? So ux comma y, the solution will actually lie on a region. X comma y is a region. X comma y is a region. Okay. So therefore, the solution of this equation is a function u x comma y, which is satisfied at every point, okay, of a region R you are seeing. So ux comma y is satisfied on region R, okay, on region R, which are seeing here. This is the region. This is that region, closed region. Maybe I can draw with this. Okay. So you can see this is the closed region you are seeing right now. Okay. Fine. This is the closed region, right? So at each point of this closed region, the solution ux comma y is satisfied. Understood? Got the idea? And what is the boundary? The boundary is the boundary condition given to you in the problem. So here, this is the boundary condition. The boundary of the region gives the boundary conditions. Okay. I hope that is okay. So boundary condition will be given in the problem. You will be given the PDE and you will be given the boundary conditions. Okay. And your job is to find the solution. You inside the region bounded by that boundary. Got that idea? Okay. Okay. So fine. Let us look into the Laplace equation. Okay, we have the Laplace equation. Consider a rectangular region R. Okay. Consider a rectangular region. Maybe I have it here. Okay. Let's consider this rectangular region. Maybe it will be easy for you to understand. Okay. So this is the region R. Okay. This is the rectangular region R. And my job is we are trying to solve the Laplace equation here. Okay. We are trying to solve the Laplace equation here. Okay. So what is our job here? Our job is we have created a mesh. We have created a mesh. Okay. So we have a region R. We want to find solution at each point of this region R. Okay. What is the best technical way to do that? Chop it off. Chop them. Okay. How you chop them? Chop them vertically, then chop them horizontally. Okay. Then you will get the intersection points. At those points, if you can find the solution, you got it. So for your understanding purpose, we have taken the grid very big, but you can actually computationally take the grid very fine. Then what will happen at very tiny step, you will obtain the solutions throughout the region, isn't it? Both vertically and horizontally, right? Then you will get the solution at each and every point of the rectangular grid, right? So you solve the PD. That is the idea. That is the idea. So we will take this grid. Okay. Mind you, it should not look this big. If you take this H very small, if you take the H very small, it will be a very fine grid. I mean, actually your grid should look like, okay. Oh. Yeah. So actually it will look like a very fine grid. Okay. Let me go back to our solution over here. Okay. Fine. Okay. So let us try to solve this PD over here. Okay. Maybe I have this one for example. This will be better to consider. Yeah. So dou 2u by dou x2 plus dou 2u by dou y2 equal to 0 and ux comma y satisfied on region R. And R is a rectangular region for this case, for this purpose below. Isn't it? Fine. Okay. Now, how can we solve it? How can we solve it? Now, the way you can solve this is by approximating the double partial derivative with the finite differences. Okay. Double finite, like you have to apply finite differences to solve it. How can we apply finite difference? Can anyone tell me? From your previous semester, scientific computing, you must know how to approximate this from finite difference. How can we approximate this? Anyone? I mean to say, how can you write this and this using finite difference? Anyone? Hmm? How can you? So see, the main idea is we will discretize the PDE. I mean, we will approximate dou 2u by dou x2 using some finite difference approximations. How are we going to do that? That's my question. Okay. So the idea is, okay, anyway, I will write it down. So it will remind you the formula. Okay. So remember that we have a step size h. Okay. And on y-axis, we have a step size k. But anyway, we will be worried about the step size h here. Okay. So we can discretize this guy as here like this. 1 by h square. 1 by h square because you have double partial derivative. Dou 2u by dou x2. Okay. You have u I minus 1j minus 2u I comma j plus ui plus 1j. Okay. What does it mean? What does it mean? You take the left neighbor, then you take the right neighbor and subtract 2 times the central neighbor. Got that idea? If you are trying to find the value for this guy, okay, then take the value here, take the value here. ui minus 1j, ui plus 1j. Okay, got the idea? So similarly, can we write the same thing? Can we write the same thing for dou 2u by dou y2? We can write plus 1 by h square. Yes. Now, observe that since we were in the x coordinate, the x coordinate was changing. The x coordinate was changing, but the y coordinate was remaining same. Right? Now, when you are taking a partial derivative with respect to y, the y coordinate will change. That means uij minus 1 minus 2ui comma j plus uij plus 1. I hope you can correlate. Now you can see that the y coordinates are getting disturbed because we are taking the partial derivative with respect to y. Isn't it? Okay. Now what I will set? I will set equal to 0. Okay. Fine. Okay. Now I am asking you the question that can we make ui comma j the subject? Can you make ui comma j the subject? What do I mean by that? Can you write ui comma j equal to something? Can you tell me the expression? You have ui comma j here. Take it on the left side. Keep all the terms, other terms into the right hand side and tell me the expression you are getting. So what you will have? Is it correct to say uij is nothing but 1 by 4? 1 by 4 ui minus 1 comma j plus ui plus 1 comma j plus ui j plus 1 ui j minus 1. Is it correct? Will h square come? You have a 0, right? H can h be 0? H is a step size, right? Can h be 0? H cannot be 0. So the other quantity has to be 0. So then h won't be there now. Not understanding. Agree. Yes. Can this guy be 0? Can this guy be 0? How many of you are saying yes, it can be 0? H is a step size. It cannot be 0. If it is 0, there is no meaning of doing PDE. Okay, so this cannot be 0. If this cannot be 0 and you are multiplying something which is equal to 0, that means this full guy is equal to 0. Therefore, you will get the Uij equal to this. Okay. Okay, fine. Now I want you to understand this part. I want you to understand this part. This part here. What can you understand from this part? If you want to find Uij, then he is telling, this method is telling that you take the average of this person, this person, this person, this person. 1 by 4 times ui minus 1j, ui plus 1j, uij plus 1, uij minus 1. Okay. You take the average of the left, right, top, bottom. Then you will get the value at the center uij. So same applies to any point you go. Same applies to any other point you go. Okay. So since this kind of formula is known as a standard 5-point formula, okay, because this formula is established from 5 different points, okay, this is referred to as a standard 5-point formula. Okay. So standard 5-point formula. Okay. Now some of you can come back and say that, is this the only way? Is this the only way? And the answer is no. There is another way. Okay. What is that another way? Instead of taking these points, I can take these points also. I can take these points also. And I can compute these. Right? I can take average of those also. Isn't it? And I can compute the center point also. So if you consider those green points, you can feel like diagonal. You can consider this as a square. You can consider this as a square and think that these are the diagonal points. These are the diagonal points, right? So if I write that formula, what should be Uij? Can anyone tell me? I'm telling like it will be average of that. So can you tell me, anyone? If I consider the diagonal points, if I consider the diagonal points, green points, what should be the formula? 1 by 4 of, can you start telling one of the green points? Suppose this one. What is that point? Ui minus 1? Yes. Ui minus 1, j plus 1. Then next point here, this one. Ui plus 1, j plus 1. Then this one. U. Yes. What is this point? I minus 1. j minus 1. Okay. Then this point, u I plus 1, j minus 1. Yes. u I minus 1, j plus 1, u I plus 1, j plus 1. Okay. u I plus 1, j minus 1, and u I minus 1, j minus 1. Okay. So you have considered the diagonal points and taken the average. Okay. This is also a formula. Okay. To compute the uij value. And this is known as the diagonal 5-point formula. Hmm. Then, huh, cannot hear. Can you hear? Can you hear? If she cannot hear, how I can hear? We don't want to find center point. I am taking a point as an example that I have taken a center point. It can be this point also. If you want to find this point, you can take this also. Diagonal 5-point. You can take this also. It is not like I am finding center point. I am taking the square grid. In that, I am finding the center. I am finding the center value based on the diagonal or the top, bottom, left, right. So what will happen? I can find any such point value in the grid. Then what does it mean? I am finding all solution of the PD in that grid. We have boundary condition. Boundary condition means these we know. These boundaries we know. Huh? Okay. Huh? Just have to? Huh? Then? Huh? So how will you find the point? You will get the point, but how will you find the value of it? Yes, we know. If you are here, by taking one step, you will be here. We know. But how will you get my energy here? How will you get the value of u here? We are not finding the location here. The location are determined by ij minus 1, ij plus 1 like that. What we are trying to find is the value of u. U is the solution. We are trying to find the value of u. Okay. Okay, so now did you understand these two formulas? So now I hope that you understand that if you can try the formula, okay. If you try the formula, okay, so then you will get two types of formulas. Okay, one is diagonal 5-point and another is standard 5-point. Okay. Which one is better? Why? After class. Okay. Okay. So you can see these examples we have already considered. Okay. Here to give you an idea. Okay. So you can see, and it is getting blurred. But you can see that if you want to find the value of this point, we can take the value in the neighbors, top, right, bottom, left. And if you want the value at this point, you can take the value of diagonals. So of course, like you can analytically show that the standard 5-point is better. The standard 5-point is better than the diagonal 5-point. Okay. Fine. Okay. So after we obtain these initial values, mind you, now we have two different methods. Okay. Now the question is, after we obtain these initial values, okay, we can improve the accuracy by using numerical methods. Okay. I hope that in your scientific computing first semester course, you must have heard about Gauss-Seidel and Jacobi method. Yes. So similar kind of method we will apply here. Okay. We will not apply the equations, but we will apply the up-to-date rule in this case. Okay. Gauss-Seidel and Jacob. Okay. So after, okay. So after obtaining initial values of u, we can further make it more accurate. We can further make it more accurate by using two things. That is Jacobi's method and Gauss-Seidel method. Okay, that we will see. That we will see here. Okay, you will see that there is not much change. Okay, there is just a slight change. Okay, in the methods. Okay, I hope that you remember that in Gauss-Seidel, you use the latest value, right? In Gauss-Seidel you use the latest value, whereas in Jacobi you don't. So same idea will apply here. Okay. Okay. So maybe we can consider this standard 5-point formula. Okay. Closely watch the standard 5-point formula here. Closely watch it. Now I am writing the standard 5-point formula in terms of the Jacobi method and in terms of the Gauss-Seidel method. Okay. So Jacobi method first. Jacobi method. Okay. Okay. So after n such iterations, okay, after n iterations, at nth iteration, I am denoting the value of uij, okay, as ui comma j n. Okay. At nth iteration, I am denoting the value of uij as uij superscript n. Okay, so that I will know which iteration it is. Okay, you will be doing iteration by iteration to get more and more accurate values. Okay, so uij at nth iteration is uij n. Okay, at n plus 1 it will be uij n plus 1. Okay, like that. Okay, then you have the Jacobi method as what? You have the standard 5-point formula uij equal to, yes, so uij n plus 1 at n plus 1th iteration, it will be the average of ui minus 1j, the left hand side, at nth iteration, plus the right ui plus 1j at nth iteration, plus ui j plus 1, the top one, at nth iteration, plus ui j minus 1 at nth step, the bottom iteration. This is the Jacobi method. Okay, where the future state depend on the past. You can see the n plus 1 values depend on the nth state. I hope that is okay. N plus 1th value depends on the nth state. Now let us look into the Gauss-Seidel method. Okay, let us look into the Gauss-Seidel method. Okay, in this method you will use uij n plus 1, okay, is equal to 1 by 4 of, there is a catch, I will write that. It is all same as your past. That means ui minus 1j left, ui plus 1j right, uij plus 1 top, uij minus 1 bottom. It is all same, but there is a slight change. Okay, there is a slight change. What is the change? Can anyone tell me? So this depends on the past, n, no issue. Okay, and you have this also depends on the past, but there is a catch is The other two values, that is the left one, depends on the latest iterate, n plus 1th. And this top one, uij plus 1, will also depend on the latest iterate. You got the idea? So this is how this should give you some glimpse of your first semester, how you use Gauss-Seidel and Jacobi. In Gauss-Seidel, you always use the latest value available. Got the idea? So similarly here, the left and the top are using the latest values, and others are using the past values n. So therefore, Gauss-Seidel will be the more accurate method here. Okay. Why? No. In Gauss-Seidel, whenever a latest value is available, you use that. No, it is not the first one. No, it is the n plus 1th iteration. It is not the first iteration. Then how you were getting that value in your first semester? Yeah, it will be also steps. While doing an example, it will be more clear. Okay, but it's the same concept almost. There also you were using step by step, you will get the latest value that you will apply. Here also it will happen like that. Don't worry. By doing an example, it will be more clear. Okay, Gauss-Seidel. Okay. So I hope we can do an example now so that it will be more clear. Maybe this one I already have, I think. Yes. Let us consider this example. Let us consider this example. Okay. So this is your region R. This is a rectangular grid. Okay. In the grid, you have been given the value of u at the boundaries. Can you see that? In the boundaries, you have the values of u. 1000, 2000, 1000, top 500, 1200, like that. Yes, those are the boundary conditions, value given to you. What is your job? Your job is to find the value of u inside the grid. Inside the grid means what is the u1, u2, u3, u4, u5, u6, u7, u8, u9. Those values you have to find. So you can start using standard 5-point formula or diagonal 5-point formula to get those. Okay. Okay. So, okay. Before beginning, what I want you to ask, what I want to tell, okay, is, do you see some symmetry in the problem? Is this a symmetrical problem? Do you see any symmetry? Hmm? Yes. Yes, yes. So if you consider this line, you can see that this value matches with this value. This value matches with this. This value matches with this. This value matches. Isn't it? Now, can you see another case also? You can see this case also. Okay. You can see this value matches with this. This value matches with this. Okay. I mean, so what? If the value matches, so what? Huh? LPG. area is more. Ball. Polarized. Whatever I am hearing, I am telling you. Cannot hear. Anyway, so the idea is they are symmetric. Okay. If they are symmetric and these values matches with these values, this value matches with these. Okay. Fine. Does it mean that U1 should also match with U7? Yes. U2 should match with U8. U3 should match with U9. Okay. Agree. Right. Now let us consider the other case. The other case is this is matching this. This is matching this. Right. Agree. So what will happen? What will happen? U1 should match with U3. Right. U1 should match with U3. Then U4 should match with U6. U7 should match with U9. Yes. Do you agree? Clear? Can we write that now mathematically to solve the problems? Okay. So what will happen? So from symmetry, what we have? We have U1 equal to U3, U4 equal to U6, U7 equal to U9. Again, from symmetry may be vertical, I am telling. From symmetry again, from horizontal symmetry. What else we have? U1 is equal to U7. U2 equal to U8. U3 equal to U9. Good. Finish. So now what does it tell? That if you can get few values, you can determine all other values. If you can just determine few values, you can determine all other values. Okay. Got the idea? Okay. So if you can just find the values of U1, U2, U4, U5, it's sufficient. It's sufficient to find the values of U1, U2, U4, U5. If you can find these values, you can find all other values. Okay. How can we find? So how can we find those values? Can anyone tell? We have to use the diagonal 5-point formula. Okay. Now here the trick is, now we have to do the first iteration. Okay. In first iteration, you can apply wherever possible, if you can apply standard 5-point formula and diagonal 5-point formula, better choose standard 5 because that is more accurate. Okay. And if you don't have a choice, suppose you don't see that I cannot apply standard 5-point formula because there is one unknown there, I cannot apply. But yes, I can apply diagonal 5-point. If there is no other choice, then apply diagonal. If there is no choice to apply standard 5-point, then you can apply diagonal. Okay. So this first iteration you can do like that. Why I am saying like that? Why I am trying to tell that point? Because we need to have some value as first iteration to begin with. Then we can refine it with iteration by iteration. Second iteration, we can refine the values of the first iteration. Third iteration, we can refine the values of the second iteration. You got the idea, right? So can we start the first iteration? So from the first iteration, can we find U5? U5, apply standard 5-point formula for U5. If you apply standard 5-point formula, what are you getting? Can we take, so apply standard 5-point formula, watch my mouse cursor, okay, very carefully. You are trying to find U5. Okay, can I take U5 as the sum of 1000, then 2000, 2000, 1000, and take the average. Take the average. Why we are doing like that? Because we don't know any other value. We don't know. You are telling that we can take U2, U4, U6, U8, but we don't know those values. So we cannot take. So we have to take some values which is available to us. Okay. So we can take these 1000, 2000, 2000, 1000. Agree? Okay. So what will I get? 1 by 4 times 1000, that is the top, 1000 bottom, 2000 on the left, 2000 on the right. Mind you, this is the first iteration. So we are playing a bit rough. We are playing a bit rough. Okay. Another value, can you find U1? Can we apply U1? But note that to find U1, we cannot use standard 5-point because we know this value, okay, but we don't know this, So we can apply diagonal 5-point. Can we apply diagonal 5-point? If we apply diagonal 5-point, yes. Why? Because we have this value, we have this value, we have this, and from your previous iteration, you already have U5. From your previous iteration, you already have U5. Now, how clever it is to first find U5 and then find U1. I could have first found U1 first and then found U5. But I first found U5, then found U1. It's a game of playing chess, actually. Which one to take one so that I can easily go? Can you see why we first found U5? So that I can use this here. 1 by 4 times 0 the diagonal, then 1000 in the diagonal, then 2000, then U5. From here, what is the value of U5? So you can put it 1500 here. So then what is this value? Yes, 1125. After this, what we should compute? Can we compute U2? Can we compute U2? How we will compute U2? U2, can we apply standard 5-point formula? Yes, we can apply standard 5-point formula because you have U1 and U1 is equal to U3. U1 is equal to U3 from symmetry, right? So U2 is equal to 1 by 4 times. If you apply standard 5-point formula, what are you getting? This value, this, then can you tell? U2 is equal to 1125 U1 plus U3 1125. Then top is 1000. Then U5 is 1500. So this value is 1187.5. Okay. 1188. Yeah, of course it won't be. Can you check again? What's the value? After U2, can we compute U4? See, I told you here already. Why are we doing this? Because you know, if we calculate these values, we can obtain all other values. And same thing we are doing here. Okay. Getting. So what can we apply here? Can we apply standard 5-point? U4. Actually, you can apply diagonal also. But if standard you can apply, prefer standard because it will be more accurate. So standard means U4 means you will apply this, this. So it is 1 by 4 times 2000 plus what is U1? So U1 is equal to U7. From symmetry, U1 is equal to U7. So 1125 plus 1125 plus U5 is 1500. So this value is 1437. Okay. So now you know, since you have computed all of this, I am happy to say that you know the value of U3, U6, okay, U7, U8, U8, and U9 also, isn't it? Okay, fine, right? Now the actual game begins. Okay. So now for second iteration, now these are the first iteration value. This might not be that accurate. So for second iteration, we can apply our Jacobi or Gauss-Seidel. We can apply our Jacobi or Gauss-Seidel, right? Okay. So can we write the formula for U1 now? U1 n plus 1. U1 n plus 1 is equal to 1 by 4 times U1. Check U1. Yes. We can apply the standard 5-point formula, I think. Isn't it? So what you will get? You will get 1000 plus U4 of n plus 500 plus U2 of n. Do you agree? Agree? Meeting. How? Are you getting the, while I am writing, are you getting that? After that, what you will find U2, can we write? U2 n plus 1 is equal to 1 by 4 U2 n plus 1. So now your question is being answered. Can you can you now see how we can apply Gauss-Seidel? Okay. Now you can, U2 depends on U1 and U1 n plus 1 you already have from the above steps. So you can apply. So it is stepwise as you put. So U2 n plus 1, but here we are applying Jacobi now for now. U2 n plus 1 is equal to 1 by 4 of what? We can apply U1 of n plus 1 if we apply Gauss-Seidel, because U1 of n plus 1 is available to us. Why don't we use the latest one? Gauss-Seidel is more accurate than Jacobi. U1 n plus 1, then can anyone tell the other one? Yes, plus 1000 plus U5n plus U3n. But you already know that U3n is nothing but U1 of n. U3n is nothing but U1 of n. Same thing you can write. Okay. After this, can you tell me what we do next to U4? U4 of n plus 1, can anyone? 1 by 4? What is U4? U4 of n plus 1. N plus 1. So 2000 will be there. Boundary. Plus. Yes. Then U7 is there. Okay. U7 of n plus U5 of n. Huh? You have use 7 of n. That can be done. But will that be the case? I think so, no? At every step, it should follow symmetry, right? We can check that. We can check. Okay, fine. Let us write as pure as possible, like without equating, just write what you are getting. Then you can later change to the easier form. Okay, fine. U4n plus 1. What is U5? 1 by 4. U5 can be 2. U5n plus 1 now depends on. Yes. Now you can apply, actually, we know U2n plus 1. We know U4n plus 1. Yes. So we can apply U2 of n plus 1 plus U4 of n plus 1. Any other case? U8 and U6. U8 and U6. U8 and U6. So actually the idea here is like you have U8 of n. You have a U8 of n and U8 is equal to U2. So U8 of n you can only replace with by U2 of n. You cannot replace it by U2n plus 1. And U6 of n. U6 of n is equal to U4 of n. So you can replace it by U4 of n. That is okay. Hmm? Okay, you are trying to tell that U4 n plus 1 we already have. Why don't we put that? Okay, let's try that. Maybe we can get it. But I am trying to say that it is n here. So how can we put that? We will directly take the updated one. We'll directly take the updated. Okay. You can try. You can try. So what you are trying to tell is without this we can put U4 n plus 1. Yes, that I think it will be more accurate. You can try. Instead of U6, no, U4 n plus 1 you can put. U4 n plus 1 we already have in the previous step. Yes, but U4 n plus 1 you already obtained. So why don't we put that U4 n plus 1? We have not computed U6 of n plus 1. It will be equal. It will equal. But okay, you put. Okay, you put. But will it be wrong if I write U4 n plus 1? No. You write U6 n plus 1, I will write U. Okay. Both of us equal value only, right? But I prefer to write U4 n plus 1. Because previous step I already computed those values. Okay. Fine. So can you start computing the iterations? This will be homework for you. Okay. Submit that. So you know that no now. So what is the idea? Put n is equal to 1. So u1 of 2 will be depending on u4 of 1, u2 of 1, right? And both of them we already have from first iteration, right? Got the idea? You can get the second iteration. Similarly, you can compute the third iteration now. Third iteration, put n is equal to 2. Then u1 of 3 you will get. Okay. Do till fourth iteration. Do till fourth iteration. We want two different groups. One group who use the past value, one group who use the up-to-date value. Okay. So I hope that is clear. Okay. What we can do is next class we can solve two different methods, Jacobi and Gauss-Seidel. Okay, so that you can get a bit more confident. Okay. But anyway, you got an idea. You got a general idea how what's the idea so far now? We have a PDE. PDE is defined on a region. Any region we can chop it and make it rectangular mesh. After making rectangular mesh, we can compute the two kind of formulas, that is standard 5-point formula or diagonal 5-point formula, right? And you can set an iteration scheme. If you have the up-to-date value, if you are using in your iteration scheme, it is known as Gauss-Seidel. If you are using only the past, even though the latest version is available, that is known as Jacobi. Then since Gauss-Seidel is using the up-to-date value, Gauss-Seidel is more efficient than Jacobi. Okay, fine. So, and we solve one problem, and this is the iteration scheme I gave to you, and it is a homework. You have to do till 4th iteration. Okay, all of you. Maybe what you can do is 2 classes. Okay, maybe this group can do the past values only. Maybe these 2 groups can do the latest value. Okay, you understood? Got the idea? Wait, shall I take? So got the idea, no? So who will do the past values? Okay. The right hand side will do the past values, left hand side and other twos will do the up to date values. We will check who did the past. So no one should do the other task not given to them. Okay, careful. Anyway, this is a method to solve Laplace equations, right? This is a method to solve Laplace equation. What we solved here actually, we did all this method. Why it was possible? I want to ask. Why this method was possible? Why this method was possible? Yes, it is equal to 0. Since it is equal to 0, you are able to write Uij in terms of other things, right? Therefore, you got the formula so nicely and easily. If the right hand side is not 0, you could not have got. Then it will be very complicated things. Actually, you can think like then you have to go to matrices. You have to go to matrices and the equation you will get is in form of Ax equal to B. Now you have Ax equal to 0. If the right hand side is not 0, you will get Ax equal to B. Okay. Then you will have a tridiagonal matrix. Then more complications come. Okay. So therefore, I think in your first semester, you know how to tridiagonal matrix. No? Did not get. Okay.